What's the big deal about this work? I think it might be the case that we propose one solution to a very elegant calculus that we like and solves a practical problem so that can be ready for wider adoption. So this is outline. So first I will show you the motivation of this work, including the background information, intersection types, merges, and show you the problem. Next, I will informally show you the solutions. And finally, I will show the calculus, including its properties, and conclude with related work and standard stuff. So here's the motivation. So Dunfield in 2012 has proposed a very simple lambda calculus extended with intersection types and term level merges, and elaborate that into a simple lambda calculus with only products and pairs. It can serve as a foundational calculus for a number of language features, including overloading and extensible records. So in this example, we define a person record and extend it with the merge operator denoted as the double comma. So later we can access the term using the age label. So what is an intersection type? So I think it's best to understand via the examples. So in this example, we have an x variable. It has type int intersect with Boolean. And we also have the standard functions such as the successor function and the not function. The interesting part is in the last line. So we create a pair that uses the x variable, but the type of x there is different. In the first example, since the successor function expects an integer, so x will be integer there, and would be Boolean in the second part of the pair. And merges is just like pairs, but it will do some magic. So if you have the merge of 1 with true, then it can be used as integer as well as Boolean. And this is the introduction rule for the merges, just like pairs. Nothing interesting here. But magic is happen when you are trying to use that merge. Because the elimination of merges is implicit, there's no need to manually extract the components out of the merge. So the type system will extract the string from the merge since the function before it is expecting a string. And the elimination happens because there's a subtyping relation between intersection types. And the subtyping relation is just like the relation for sets. So int intersect with string is a subtype of string. And under the hood, there will be a coercion generated so that the string will be extracted from the merge. So here's a quick summary of the merge comparison between the merge and pair. Introductions are the same, and elimination, if you have a merge, is more convenient to use than pair. And also, in a merge, you shouldn't really care about the order of the components appear in the merge, whereas for pairs, you do. But unfortunately, there is one problem with merge. Since the order does not matter, the only information they can use is the type. So what happens if the types are the same? So we can go through the examples. And the first example is OK, because int and Boolean are different. So if you want to use the merge as integer, it's clear you want 1. And if you want Boolean, that's true. But if you want an integer out of one merge of 2, then there are many possibilities of design choices. So Dunfield's existing calculus allows this incoherence, and we call this incoherence. And that's the starting point of our work. So having seen the integer and integers, one quick solution is to forbid overlapping types. So naturally, we want base types, such as integers, string, and Booleans are disjoint. But what about more complicated types, such as two function types, or integer with a function type? And this is the key definition of disjointness. So we say that two types are disjoint if they do not have a common supertype. And this is the formal definition. So let's see some examples. In this page, there are 3 examples, and it's basically just functions between integers and strings. And actually, the first example, the 2 functions types are disjoint because you cannot find a type that is a common supertype of the 2. And the same applies to the second example. But the interesting part is the third example. Because we can find a type that is actually a supertype of both of them, which is integer and string, and the codomain is string. Since there's contravariance of the function type here, so you can see this violates our definition on the previous page. So the 2 types are no longer considered disjoint in this case. So is that the end of the story? Unfortunately, it's not. So disjointness is not enough to guarantee coherent semantics. So we can consider this function application. The function and the argument, they both have a disjoint type. But unfortunately, there are many ways that you can invoke this application. So it can be 4 if you want to use the successor in 3, or false if not and true. And this is actually the other problem besides the disjointness problem. And this is the problem of type ambiguity. And our approach is to use a bidirectional type checking. And in our bidirectional type checking rules, the type system will detect such kind of ambiguity and requires annotation on the side of programmers, so that if there's no annotation there, the program will be rejected. So in summary, the solution is a disjointness plus bidirectional type checking. And the two have different purposes. The disjointness will ensure the extraction from the merge is unique, while the bidirectional type checking will ensure that there's no other bad cases. So this is the central theorem of this calculus. There are 2 statements there because we use the bidirectional type checking, but the spirit are the same. So what this theorem says is that if you have elaboration into a target language, then elaboration result must be the same. So it says that there will be a unique elaboration result in the target language. So here's the syntax of the language. It's quite simple. It's just like downfield calculus. We have a simple lambda calculus extended with like base types such as integers and also products. And for terms, we have a merge. So excluding the shaded part, all the stuff are standard. And for the type system, we require the intersections and merges to be disjoint. That's why it is called disjoint intersection types. And we add the disjointness constraint in the well-formedness of the intersection types, as well as the formation rule for the merges. And the semantics is defined via a type-directed translation so that intersections will be removed and become products and merges into pairs. And for the merges, the magic actually happens because there's a coercion generated for the subtyping relation. And the coercion is actually just a function that extracts the pairs in the target language based on the type. But the problem coherence really comes from partly from the multiple coercions. So in this example, if you have 1 merged with 2, then since there are 2 possible subtyping relation, and the coercions are different, and this leads to different target terms and different evaluated values. So how to solve this problem? So this is the simplest rules for intersection types. But there are a lot of overlap here, so it can yield different coercions and leads to the problem of incoherence. What we do is we identify two types of overlapping and remove them via different techniques. For rule overlapping with 2 and 3, we require that some type in the induction rules to be ordinary. And by ordinary, we mean that the type are just not intersection at the syntax level, so that the first rule can always take precedence over 2 and 3. So there is no ambiguity. But there are also the second type of overlap. The 2 and 3 overlap themselves. And this is where the disjointness comes into place. And the result is that we can ensure that during any derivation of a good program, it's not possible for you to be able to apply rule 2 and 3 at the same time. And this will ensure that there's only one possible coercions. Since we have solved the type 1 and type 2 overlapping, we now have the lemma of unique coercions. So it says that if A and B, they are a subtype of one of another, and they're well-formed, which basically means they respect the disjointness constraint, then the coercions must be unique. But there's one thing that we haven't done yet. This is the disjointness judgment. Since the definition is not algorithmic, it's not clear whether we can actually implement the calculus, because there's an existence thing there. But luckily, we also have the set of rules that are equivalent to the definition, which is sound and complete. And there are many rules. For example, you want integers and string to be disjoint. And this is the rule for functions. It's quite interesting because we don't use information on the domain part, only the codomain part. So two function types are disjoint as long as their codomains are disjoint. And this is actually the direct result of function subtyping and definition of disjointness. So we can use that rule to check whether two function types are disjoint or not algorithmically. So we can revisit our examples in the previous slide, and we can apply the rule and to see that actually the third example violates the disjointness constraint. So the answer is no. But for the first two, you actually cannot find the counterexamples, so they are considered disjoint. So there are a bunch of related work in this line. So Reynolds has proposed the merge operator in his calculus, and Peirce introduced the idea of elaborating the intersection into products. What is most closely related to our work is Dunfield's work. The difference is that he also considers union type, but he also leaves the coherence as a open question in his paper. Because Castagna also has coherence. His calculus in 1992 also has coherence, but it's more restrictive version than ours, because here we are considering a calculus that allows unrestricted merges as long as the semantics is unique. But in Castagna's work, he allows only merges of functions. So our work can be thought of as an extension of Castagna's work. And also, there are many languages nowadays that support refinement intersections, but not many of them have term-level merges, so they do not have the problem of coherence. You can see actually the problem of coherence comes from the term-level merge. So this is the summary. We have presented a very simple calculus that has a merge operator at the term level, also intersection types. And we proposed the definition of disjointness to solve the problem of incoherence. We have a very simple specification of disjointness. Two types are disjoint if they do not have a common supertype. And also the algorithmic rules that you can use in your implementation. And more in the paper, there are different variants of the disjointness constraint, because for some type, you might want top in your type system if you are a fan of OO programming. And our calculus is also able to cater to that. And we also have the complete theorems, the lemmas for all those different versions. So there are many directions for future work. Currently, we are considering adding union types to the calculus, so it will become even more closer to Dunville's calculus, but enjoy the property of coherence. And also, one area is naturally is a parametric polymorphism. But the challenge is that instantiation can break the well-formedness of types, because in the parametric polymorphism, there's a type variable, and you do not know beforehand if a type is really good or not. So this is the future further resources. There's a paper online, and we also have the COP proofs and the Haskell implementations for the system, so you can try that out. And all the major theorems and lemmas are proved via COC. And thank you. I'll leave time for questions.
We have plenty of time for questions. There's one here.
Phil Wadler, University of Edinburgh. So you mentioned a relationship to Castagne's work. As I recall, that's about doing overloading. So typically you might want to have an int to string and a string to string function, say for show. And I think he permits that. Am I remembering correctly?
Yep.
And you don't?
Yep.
So when you said that you generalize Castagne, what you meant is you don't generalize Castagne.
I think we took a different approach. And so now because we are using a call by value language, and we want to overloading as well as coherence, then you might be in the situation where the function application happens more than once. So we are not considering that now.
Right, so I'm correct in thinking that you don't really generalize Castagne because you can't embed what he does into what you do.
Yep.
Right, so Castagne's stuff, I knew why I might want that system. Your stuff, okay, you're fixing something in Dunfeld, but why would I want that system? Why would I, yes, it's coherent, but why would I want it?
Oh, actually, in our version of the paper, we have shown that you can create a very simple OO language that uses this feature to have extensibility. But the example is not shown in this presentation.
But you could just formulate something with records, say, directly, rather than basing it on intersection. So what do you gain by having intersection rather than working with records?
Because the merge and intersection are more general than the records. Records are they're a specialized calculus for records. But our system is, you can merge everything.
Yeah, because all the time I want something that's both an integer and a bool. Okay, thanks.
Thanks.
Thomas Schrijvers, University of Leuven. The example you've shown on slide 13 shows a case where you have an intersection of two functions and two arguments. And you choose to only apply one of the two functions to one argument. Why don't you apply both functions simultaneously? So you get, as a result, an intersection of an int and a bool?
Yes, it's possible. I think it's a design choice problem. So you can have the result being, say, 4 merged with false, but the evaluation will happen twice. And sometimes you don't want that. And our calculus is called by value. We've thought about this problem, but we did not take that approach. It's a very good question.
Stephen Dolan, University of Cambridge. So I very regularly want this. If I'm writing programs in a dependent language, I've got a function which operates on numbers, and I have a number that I know to be prime. And that's generally represented as a pair of a number and a proof that it is prime. And in order to pass my number that I know to be prime to my function that wants a number, I have to do some really tedious projection and unpacking, or maybe repacking into the collection of things this function wants. So I was wondering, have you thought about what would be needed to get this sort of stuff into a dependently typed setting?
Yes, I think there is a line of work in our team, but I'm not working on that. Yeah.
Okay, thank you.
Yeah.
So I'm Simon Peyton-Jones. It's clear from what you say that this kind of system could be done, but I guess I'm wondering is, do we want to do it? That is, have you been lying awake at night thinking, I really want to write this program, but I just can't? And that's why you did this. So I guess, Stephen, you gave sort of one answer was, if you extended this to a dependently type program, then there's a class of programs you might be more convenient to write. But had you got other programs that would just be much more convenient to write if you could have this system?
Yes.
And can you give an example? Yeah, so, okay, great answer. Great answer. But a little follow-up question. Can you say any more, like give an example?
I think the main idea of this work is that sometimes there's no ambiguity in the program. The programmers need to write a lot of boilerplate to insert somewhere. So it's better the type system can automatically figure that out.
Okay, but you don't have any particular programs in mind? Like ML programs or Haskell programs or Idris programs that have all this boilerplate?
Yes, that might happen if you want to extend the existing program. Then you might want to changing the types.
Masashiro Yasugi from Kyushu Institute of Technology. Do you include union type also, or just intersection type?
But currently, the system only has intersection types.
So maybe introducing union type can solve some of the problem for example, the intersection of int to string and string to string.
Yeah, I think for the overloading example, if you have union types, then it can be more simple to write. We've currently working on the union types, but there is also a lot of incoherence problem that is introduced due to the union types. So I think it might be a good direction.
Thank you.
Let's take any further questions offline. Thank the speaker again.